So, okay, I think we can start. So do you have any questions before we start? Either from homework or lecture, what is this, week 3? Yeah. So, okay, so let me discuss the assignment questions then. I think both week 1 and week two's deadlines are over, right?
Yeah.
Yeah, so okay. Um, yeah, okay, let's do it. So let's start with a week 1 assignment. So yeah, these are like a simple problem. So
Yeah.
this is one of the useful inequalities, right? E power x is greater than equal to 1 plus x. It's used a lot, and it's a equivalent inequality that x is greater than equal to log 1 plus x. So yeah, these. Okay. I mean, yeah, the second one is valid only when log is defined. So the first inequality is this. The second inequality is log 1 plus x would be something like this, and this would be x. So this is like used a lot. I mean, throughout the course, we'll use these inequalities. Okay, the second question is, yeah, it's again easy. It's like if x1 to xn are independent and identically distributed. So since they are independent, you can just sum the variance, right? And so, I mean, so B is one of the answers. And then when you divide by something, the variance gets multiplied by the square of that thing. So, right? And so like variance of alpha x is alpha square variance of x. And so, yeah, so which is why we get this D as well. Uh, yeah, I think there's nothing else here. Great. So, yeah, again, independent normal random variables. So N01. Okay. And you have computed the sample mean, and you want to find this confidence, you 1 minus delta confidence interval. So, so yeah, it's something like you have this distribution. Um, so mu hat would be what? It would be a normal distribution with mean mu and variance 1 by n. Okay, the variance comes from the previous question. So your estimator will have this distribution. And so if so and this mu is unknown. So your estimator will have basically this distribution, and you want to find an interval so that with high probability your that interval contains the mean. So basically we have this interval, and if we do something like we just ignore this lambda by 2 intervals, and we suppose this is mu minus a and this is mu plus a. Okay, then mu minus, so mu hat, so what we have is mu hat lies between mu plus a and mu minus a, with probability greater than equal to 1 minus delta. So, and which implies that mu lies between mu hat minus a and mu hat, sorry, mu hat plus a, mu hat minus a, with probability greater than equal to 1 minus delta. So, so basically your interval, your high confidence interval will be mu hat minus a and mu hat plus a. So, so this is basically the interval. Uh, so in general, if suppose you have an estimator and you know the guarantee that estimator is within original plus a1 and original minus a2. So what does this imply? That mu is greater than mu hat minus a1, and this would imply that mu is less than equal to mu hat plus a2. So your high confidence interval would be mu hat minus a1 and mu hat plus a2. Okay, so Yeah, there's a reversal of A1 and A2, the role of A1 and A2. So okay, so now yeah, so you need to have a bound on you want a bound on this tail, and um, so the first answer is by Chebyshev's inequality. So Chebyshev, yeah, because the variance is 1 by,
before. Yeah,
yeah, 1 by n, so the standard deviation would be 1 by root n, and this 1 by delta error,
yeah,
so that is by Chebyshev. The third is the exact thing that would come from, so where we know that for the standard normal, if this is like n01, then q of t is defined as this thing. So q of t is the tail, and right. So now this is for the standard normal. So for this is not standard normal. This is like this has variance 1 by n. So what will happen is that this tail. Uh, so okay, suppose this is the new thing, and this has variance 1 by n. Then this area, it will just becomes root n t. Yeah, so suppose, okay, so probability that z greater than equal to t is q of t. This is by definition, where z is the standard normal. And so probability of z by root n greater than equal to t is what is probability z greater than equal to root nt, which is q of root nt, right? So this is why for the when the variance is 1 by n, this tail probability will be q of root nt. And so we want this q of root nt to be less than equal to delta by 2. Okay, so that would mean that root nt would be greater than equal to q inverse of delta by 2. And the inequality changes here because q is a decreasing function. As you increase t, the tail keeps on decreasing. So inequality reverses. And so t would be 1 by root n q inverse delta by 2. So that is why we get this q inverse delta by 2 by root n. So this is the exact thing. Uh, and again, so B comes from the usual Chernoff thing. So yeah, B comes from the fact that this tail is basically e power minus t square by 2. Probability that x is greater than equal to t is less than equal to e power minus t square by 2 when the variance is 1. So uh, so yes, and so this is what gives B. Okay, and D is obviously incorrect because heuristically we know that the empirical mean and the original mean, it would lie the difference would be of the order standard deviation of this estimator, because this estimator is unbiased and its variance is like 1 by n, so things should be around like 1 by root n. So all these options have like 1 by root n, uh, and it is only the delta part which gets better if you use better and better inequality. So you used Chebyshev here, you use like Chernoff bound here, and you're using the exact tail probability here. So we get a better and better bound. And this is like 1 by n. So this is like highly concentrated. So this cannot be true. So yeah, so D is not correct. Okay, so now for the fourth one. So fourth one is like just the usual computation. You need to first so exponential distribution, exponential of lambda distribution. What would that be? It's like fx of x is e power minus lambda x. Yeah, and then there's this lambda to make the area 1 for x greater than equal to 0 and 0 otherwise. Okay, so this is the exponential distribution. And now if you want to, so to apply Chernoff bound, what is Chernoff bound? So probability of x greater than equal to t, it's basically less than equal to, so So Markov would have given us like expectation of x by t. Instead of that, we just, sorry, what is happening? Yeah, instead of that, we have like e power, or lambda is already there. So e power alpha x by alpha t, where alpha is greater than equal to 0. So this inequality is true for all alpha greater than equal to 0. Okay, and this is basically a Chernoff thing, and this is also written as, sorry, e power alpha t. This is also written as minus depth of this log homogenerating, and this is valid for all alpha greater than equal to 0. And if you want the tightest possible thing, you choose the best, the highest possible numerator, I mean excluding the minus sign. And so you want to maximize over lambda greater than equal to 0 alpha t minus log. So this is just to get the best alpha, best possible inequality through this method. Okay, so we need to find this log moment generating function, and for exponential it's very easy because it's like just lambda. This is the PDF, and we want to find the expectation of e power alpha x in dx. So this is just lambda e power minus lambda minus alpha x dx, which is lambda by lambda minus alpha for alpha less than equal to lambda. Okay, so this moment generating function exists only for some alpha, but we are okay with that because this inequality holds for all alpha greater than equal to 0. So any alpha would be fine here, and yeah, so here it's actually the maximization we have like alpha greater than equal to 0. Okay, so now just okay, and now what is this? What role is this playing? So the thing is, for this x, expectation of x is 1 by lambda. Okay, and so suppose you want to you are maximizing over lambda greater than equal to 0, which is a constraint alpha greater than equal to 0 alpha t minus log expected value of e power alpha x. Okay, this is the constraint maximization problem. So an easier problem would be the unconstrained problem, that max alpha in real number alpha t minus log expectation e power alpha x. And this is easier because for this we know things like just take derivative and set it to 0 and things like that, right? So uh, and this condition allows us to do that, that for t greater than equal to 1 by lambda you can actually make your constraint problem unconstrained, right? And this comes from basically Jensen's inequality, because we know that alpha minus log e power alpha x, so we know that this part is greater than equal to expected value of log e power alpha x, because log is a concave function. And so yeah, so this is Jensen's inequality, um, which means that this alpha t minus log thing, this is less than equal to alpha into t minus expected value of x. Okay, so this would be just alpha expected value of x. So what this means is that, okay, when t is more than expected value of x, this is positive, so we don't worry about that. And then what happens for alpha less than 0 is that this becomes negative. This whole quantity is less than 0 for alpha less than equal to 0 and t greater than equal to expectation of x. So okay, so which, and now that, and we also know, so okay, so uh, we know that this quantity is less than 0 for alpha less than 0. We also know that for alpha equal to 0 this quantity is 0, which means that if you want to take maximization, you can take over entire domain, right? Your maximization of alpha greater than equal to 0 would be same as maximization over alpha over all real numbers, because for because anyway for alpha less than 0, it's less than equal to 0, right? So you wanted to find maximum in this part initially, and now you've argued that here it's already less than whatever this part is, so you can just extend over the entire domain. So this is the basic idea. So you can just, so this condition allows you to make this problem unconstrained, and so you can just now use derivatives and things like that and find maximum, and then substitute that alpha here, and that would give you the whatever the answer is. I think it's A here. So yeah, and yeah, so it's basically giving you this exponential decline, but you also have this some linear thing here, um, which is okay. Yeah, this is basic probability question. So if x is normal, what is x square, right? It's chi-square distribution with, yeah, whatever. So yeah, you start with like probability that y is less than equal to t is same as x is less than x square is less than equal to t, which means x should be between root t and minus root t, right? And so on. So this will compute, that way you'll compute a CDF and then differentiate it to get the PDF. And so yeah, this is basically the answer. You get this, and then if you substitute the value of fx here, you get this. Okay, so here fx of x is e power minus x square by 2. So if you just substitute here, you get e power minus x by 2. Yeah. Okay, so this question is basically it's justification for the name moment generating function, right? So if you differentiate this with respect to t, so you can treat x as constant here, so x will come down, so it would just be x e power tx, right? And if you just substitute t equals 0, you get expectation of x, right? And then keep on doing this, keep on differentiating, so n times, to differentiate this n times, you just get e power xn. You're differentiating with respect to t, and e power dx. So x acts as a constant every time when you differentiate. And again, so if you put t equal to 0, you get, yeah, expectation of x power n. So yeah, so just compute this. So basically, we want to, uh, yeah. So if suppose this is f of what, f of t is this, then you want to find basically f of n, where n is this n times differentiation. So yeah, this just gives you a factorial n factorial by lambda power n. Okay. Yeah, and the seventh question is it's basically to hammer home that earlier idea that if you have certain things, you can basically make the constraint problem unconstrained under certain conditions. So what we have here is we have some function, and then yeah, so suppose like this is 3, this is 4, this is 5. So we know that f minus 1 is 5. Okay, so it's 5 here. Fx is less than equal to 3 for every x less than minus 1. So yeah, function can be something like this or anything, but it's less than equal to 3. And fx is less than 4 for x greater than 1. So this is plus 1. For x greater than 4, it's, yeah, for x greater than 1, it's less than 4. And then we don't know anything about what happens between minus 1 and 1. So the first question is, if you minimize between minus 1 to 1, it's same as minimizing over the entire thing. So yeah, so this may be correct, this may not be correct, right? So if we suppose we knew that between minus 1 and 1 fx was above 4 or something, then that would have been, no, so first would only hold if like we knew that this, okay, so okay, first may or may not hold, okay, we'll come to that.
Yeah,
Second is
yeah, yeah.
yeah, so
So
maxima over minus 1 to 1, um, is the same as maximum over the entire thing. And this is true because between minus 1 to 1, we know that there exists a point where it takes value 5, right? And this 5 is already greater than this all the x values on the left side and all the x values on the right side. So even if you include this part of the domain, 5 will still dominate it, and so basically you can, if you want to maximize between minus 1 to 1, that is same as maximizing over the entire domain. So yeah, that is why B is correct. And okay, so C is the minimum over x minus 1 to 1, fx is less than equal to 5, which is true because I mean it's 5 at minus 1. So and you are taking you're minimizing over x minus 1 to 1, so it can only be less than 5, the minima.
Sorry.
So we want to compute the minimum of fx between minus 1 to 1, right? And we know that at a particular point in minus 1 to 1, it's already 5.
Mm-hmm.
So now the minimum would have to be less than equal to 5.
Yeah, yeah,
So that is the, and d is the maximum is less than equal to 5. So again, we know that at some value it's 5. So what that tells us is that maximum is greater than equal to 5, because it could be that fx is something like this, right? So this D option is again not correct. So yeah, but yeah, this is the kind of logic we used earlier to expand to the domain of optimization. Okay. Yes, the AS problem we already discussed last time. So we have this probability that yn greater than equal to 10 power 6. We are interested in this quantity, which is like, suppose this is fn. We know that by Markov, this is less than equal to n by 10 power 6. So n is the expectation of in, right? So fn is less than equal to n, and then we want n such that fn is greater than equal to 3 by 4, right? So for what n would this be true? And and so this is what we discussed, that yeah, you take at least your step size is less than this, n by 10 power 6. So you need at least some number of steps to reach 3 power 4, right? So basically you need that. So this is your how many, what is the maximum step size, what is the maximum value you can reach after n steps, that is 10 power 6, and we want this to be greater than equal to 3 power 4, and so n has to be greater than 3 power 4 into 10 power 6. So yeah, this is this inequality. Yeah.
but I have doubt in this.
Huh?
But I don't know. I have doubt in this. Like any value greater than this may not satisfy the given inequality, right?
Yeah, so this is true. So this is why this says that this is just a lower bound on n star. So what we have is that n star is greater than equal to 3 by 4 into 10 power 6. Okay. So n star is our quantity of interest, and we know that n star is greater than equal to 3 by 4 into 10 power. That's all we are saying. It could be strictly greater than, it could be equal to, yeah, it could be anything. So so that is why, yeah, so what you're saying is correct, that so okay, so what field do you work in? Like what is your area of research or general thing?
Mm, mostly on radar estimation.
Okay, so okay, yeah, estimation. So it's like, yeah. So in estimation problems we have this thing called sample complexity. I mean, we could have things like that. So wherein you want to achieve, you want to estimate a certain quantity within, say, epsilon, right? And then the sample complexity is how many samples do you need to do this. And so the general technique is you come up with an algorithm, right? And then you prove the guarantee of that algorithm, that this algorithm can do the required task in these many steps. So that would give an upper bound, that how many samples do you need to do this estimation. Okay, and then the other part is the lower bound part. So lower bound part will tell you that no matter what algorithm you choose, right? You at least require these many samples to estimate this quantity. Okay, so that would be the lower part kind of thing. So in general, how we prove lower bounds is something like this. So um, okay, no, so that would be a big digression. But the thing here is this, that you have this. It's again the if you want to reach this 10 from 0, and we know that step size is something, but we don't know this exact value because this exact value is very difficult to compute. We only know that that is less than equal to 5. The only thing this we can get easy, suppose by Markov or something. And so right, so based on this we can say that we need at least 2 steps,
Mm-hmm.
right? And so n star is greater than or equal to 2 hops. Okay, and this is because, yeah, so in actuality we'll need more steps.
Yeah, yeah,
This will only be true if your this 5 is exactly the step size,
yeah, yeah,
but you'll need, so that is why this gives a lower bound. So and this is the logic basically. So in basically in information theory, you prove lower bounds like this. So you have some quantity called, say, mutual information, and you will say how this mutual information grows with number of samples. You have an upper bound on that, and based on that you will say that okay, you need at least these many samples to do your task, because mutual information is less than equal to some n times something, right? And so this is, yeah, related to that kind of, I mean, the kind of argument is the same. So yeah, so it's just a lower bound. We are not saying that this you will achieve this, but you have to invest at least this much of work is yeah. Okay. Yeah, okay, so this is just for that part where we go from probability of x greater than equal to t is less than equal to probability of lambda x is less than equal to lambda, like this kind of arguments which we did for Chernoff bounds. So the basic thing that why this less than equal to and why not equal to and things like that. So we have this set of all x which are greater than equal to t, and we have another set where for all x where phi x is greater than equal to phi t for some function phi, and then we have to say which of the following are true. So if phi is strictly increasing, then a equals b. So this is okay. So x greater than equal to t, it implies that phi x is greater than equal to phi t. Okay, uh, right, and this would have been just non-decreasing. But we also have that x is greater than t is phi x is greater than phi t. If x is strictly greater than t, phi is strictly greater than phi t. So basically, there's a one-to-one correspondence between x and t. And so if phi is strictly increasing, then these two sets A and B are equal. Okay, it's just a mapping which, yeah. So if phi is non-decreasing, then A is a subset of B. So again, this comes from this part that x greater than equal to t implies that phi x is greater than equal to phi t, right? So in general, when you have this implication, this means that this set is a subset of this set, right? A smaller set implies the bigger set. So if you have like, right, so suppose this is A and this is B, so x in A implies x in B, right? So smaller set always implies the bigger set. So yeah, if in so yeah, uh, so okay, so B is true. Now if phi is strictly decreasing, then A complement equals B. So okay, so what does this mean? So x greater than t would imply that phi x is less than phi t. Okay, so this is strictly decreasing. Okay, so we know that, so this is the A complement set, uh, and this is actually B complement. So A complement would be equal to B complement, but here it says A complement equals B, so this is wrong. And finally, if phi is strictly decreasing, then A complement is a subset of B. Okay. So sorry, what did I say? So okay, so there's some mistake here. So what I wanted to say is that if x is less than t, then phi x would be greater than phi t strictly. This is because of strict thing. And this is A complement, and this is not B actually. This is like this is smaller than B. B is a bigger set because B also has this equality part here, right? And this is this, and so this is given by D, that if phi x is if phi is strictly decreasing, then A complement is a subset of B, because we will have this equality here. Okay, okay, and this finally we have this: suppose a random variable satisfies this condition. So it's basically the log moment generating function of x square, and for lambda equals 2. We know that this is 10. Then the question is, can we claim anything about variance or yeah, second moment? And so here again we use Jensen's inequality, that log of expectation uh, of e power 2x square. So log is concave, so if log is outside, it will be bigger. It will be expected of value of log of e power 2x square, which is equal to expected value of 2 expected value of x square. So, and we know that this is equal to 10. So what we have concluded is that the second moment is less than equal to 5. Okay. Uh, and we know that variance of x is always less than equal to the second moment. And so yeah, both B and C are true. So this was just Jensen's inequality. Okay, so these were week 1 questions, and now we'll look at week 2 questions. So for week 2, first question: let x be a real valued random variable, f be a function. Which of the following are true? Okay, so you know this characterization of variance, right? Variance is like, for any random variable y, variance of y is minimum over y, y minus y, the whole square, the the mean square error. So basically, what is your best deterministic estimate of this random variable y? So that is, and the solution to this comes out to be y equals expected value of y. So if you don't see y in, right, the best estimate is like just the expected value of y, and so y star here. So which means that if you want, if so, this is like the best possible mean squared error. But if you just want some upper bound, you don't care about the exact thing, you can just take any y, and this will hold true. Okay, this holds for all y, all possible y's. Uh, so yeah, if you take any arbitrary y, your mean squared error would be greater than this the variance of y. So this is the thing. So what we can claim is that for any given real number alpha, variance is, or this mean squared error when you estimate fx with alpha, is just greater than variance of x. Okay. So yeah, so this is a useful thing for upper bounding things, and I think we used one of these things while deriving for Hoeffding, used in Hoeffding lemma. If you see the derivation of that, we use this fact. Okay, so second question is, if x1 to xn are random variables which are not necessarily independent, so it can be anything, and xi lies between 0 and 1, which of the following are true? And mn is this empirical average. So okay, so for independent we know that, okay, if independent, we know that variance of mn would be, since we are multiplying by 1 by n, the variance would multiply 1 by n square, And since these are independent, the variance would be summed, variance of xi. Okay, if independent, but they are not necessarily independent. So what can we claim? Um, so okay, so first of all, if they are not independent, then you can obviously come up with examples where variance of mn is less than equal to uh, this variance, variance of. So basically, you want to come okay variance of, in essence, you want to come up with examples of variance of x plus variance of y, right? So okay, so this will be true when x and y are like negatively correlated. So for instance, suppose x is equal to minus y. Yeah, this is the what this is the like deterministically negatively correlated, right? If you see x, you know that y is minus x. So in this case, variance of x plus y is just 0 because x always cancels y. They are so negatively correlated. But variance of x and variance of y separately would be some positive numbers. So it could be like sigma square, sigma x square, sigma y square. Okay, so A may not be true. A is not always true, basically. B is that variance is greater than equal to this thing. So so again you can this will again this variance of x plus y, it can be greater than variance of x plus variance of y. So this was true when x y were negatively correlated, so that they cancel each other out, and so the overall quantity becomes small. Here we could have like positively correlated random variables. So suppose x equals y. Okay, so this is like total correlation. So in this case, variance of x plus y is just variance of 2x, which is variance of 4 times variance of x. Whereas this thing is just variance of x plus variance of x, which is 2 variance of x. Okay, so we have come up with an example where variance could be higher than the sum of variances. So again, so this is not correct. Uh, C is variance is less than equal to 1 by n. So this is just, again, you can just use the examples for part A. You can show that this may also not be correct. And finally, we have that variance is less than equal to 1 by 4. And this is correct because we know that Mn lies in 0, comma 1. And for any, so right, so for any random variable lying between a comma b, we know that variance is less than equal to b minus a the whole square by 4. Okay, this was again this was used in Houghton's lemma. Right, and Houghton's lemma basically gives you that for any random variable x in a comma b, you have that this moment generating function e power lambda x. Okay, this is less than equal to e power lambda square by 2 into the variance factor, and the variance factor we just said that it came out to be that variance is less than equal to b minus square by 4, and so we have this lambda square b minus a square by 8. Right? So this was Houghton's lemma. So just based on the fact that it lies in certain range, we can claim this, that the variance would be less than equal to 1 by 4. Okay, so third question: f is twice differentiable, twice times differentiable. Okay, so which of the following are true? So A is like if f dash x is greater than equal to 0 for every x, then fx is greater than equal to 0 for every x. So again, right, just it's an increasing function, but increasing function can be negative, so A is not true. Uh, but B is true, that if fx is 0, and we know that f dash x is greater than 0 for x greater than equal to 0, then fx is greater than equal to 0 for x greater than equal to 0. So you can prove this using mean value theorem. But the thing is, yeah, if you're starting at 0 and your derivative is positive, you can only go up. So, yeah, so B is correct. C is f of 3 is f of 0 plus, okay, so C and D just Taylor, to test your Taylor knowledge. So f of 3 is f of 0 plus 3 f dash of 0 plus 9 by 2 f double dash of 0. So again, this may not be true. what is true is this D part, which is that f of 3 is f of 0 plus 3 f of f dash of 0 plus 3 square by 2 f double dash of a for some a in 0 comma 3, right? And so this is Taylor's theorem basically. And and now if you have some guarantees like f dash a is less than equal to say 1 for all a in 0 comma 3, then you can get some guarantees. So yeah, but the original Taylor theorem is this. Okay. Okay, so yeah, so this is Radon Nicodemus theorem. This is something we discussed last time. So let x be a random variable taking values in this 1 to n. So discrete random variable. Uh, P is a distribution with this PMF, and Q is a distribution. We only know that Q satisfies this. So Qx by Px is alpha e power 5x, where alpha is some constant. So what is the value of alpha? So this is just computing the normalization constant. So this means that Qx is alpha e power 5x Px. Okay, and this should hold at Qx should be equal to 1. So basically alpha e power 5x Px should be equal to 1. And so alpha is just 1 over e power 5x Px. Okay, which is basically just the expected value of e power 5x. So with respect to p. Okay, so this defines a new distribution. This is so q is exponentially tilted version of p. Okay, we just say this, and this doesn't mean anything on the domain. So domain is still 1 to n for both p and q. It's just that the PDFs change. So if p is something like this, q may be q will make something some bigger, some smaller, yeah, based on what x is. And yeah, and so that it's just a different distribution. Okay, and the normalization constant is, yeah, just to make it fun. So and this is something why this Radon Nicodemus derivative is useful. So so same setting as above, EP and EQ denote expectation with respect to P and Q respectively, which of the following are true. So okay, so Q and P are different distributions, but the only thing we know is that Qx by Px is alpha e power 5x. And so yeah, A in general will not hold. But what will hold true is that if you want to take expectation with respect to Q of any function fx, okay, because of this formula here, because of this relation here between Q and P, you can claim that this is same as taking expectation with respect to P of fx into, yeah, alpha e power 5x. Okay, and I mean in this case you can just see it clearly because it's just this, and RHS would be what? It would be Px fx, and this alpha e power 5x is again, this is Px, this is Qx by Px. And so basically Px cancels, and you have that LHS and RHS are the same. So for any function this holds true, and so B is true. C is one of those confusing things where, okay, you multiply the Radon Nicodemus derivative with the, I mean, you take Radon Nicodemus inside the function itself, which is not the way it works. So C is not correct, and yeah, D is also incorrect. So yeah. Okay, so we have this question about a fair coin is tossed 1,000 times. Let alpha be the probability that heads appears at least 600 times. Then which of the following are true? So okay, so A and B are just the usual, right, binomial things that uh, so probability that heads appears at least 600 times. would be if 600 to 1000, from 1000 choose k, right? And then half power k and half power 1000 minus k. This is the probability. Okay, number of heads is at least 600. So which gives b, and a is same because of this property of the binomial coefficient. Uh, and yeah, and then you can use Chernoff bound to claim this C and D. So Chernoff bound also gives you a way to handle this term, this binomial coefficient. If in some problem you are confronted by this kind of equation, this kind of summation of binomial coefficient, then you can use Chernoff bounds by interpreting as the number of times heads appears and tails appears. So what will Chernoff bound say? Chernoff bound will say that probability of average, this minus mu, uh, this probability is greater than equal to t, with this probability is less than equal to 2 n t square. And and we know that this is this is actually the number of times heads appears. Mu is half because it's a fair coin, and we want that heads appears at least 600 times. So we want that 1 by n xi is greater than 600 by 1000, right? Which basically means that 1 by n xi minus half, we want it greater to be 1 by 10. So this fraction is 1 by 10. And this Chernoff bound gives you that this probability is, so this then e power 2 into n is 1000 into t square, so 1 by 100, which gives you e power minus 20. So alpha is less than e power minus 20, which, so basically you have that 2 power minus 1000 k equals 0 to 400, 1000 choose k, right? This is less than e power minus 20. And so so you have basically an upper bound on this binomial coefficient based on by using Chernoff method. So Chernoff method is also this combinatorial aspect to it that you can link it to these combinatorial numbers. Okay, so the seventh is x1 to xn are some random variables satisfying something. So this is same as e power lambda summation of x, right? It doesn't need independence or anything. This is just the property of exponential. And we have a bound on the moment generating function of summation of xi. Okay, so then which of the following are true? And this question is again just to emphasize that once you have a bound on the moment generating function, you don't need to know anything else. I mean, everything follows the subquotient bound. So if you have this kind of moment bound on moment generating function, so if you just follow this thing, use the Chernoff method and everything, you get that, right? So if we know that e power lambda x is less than equal to e power lambda square v by 2. So if this holds, then by Chernoff method, we get that probability that x is greater than equal to t is less than equal to e power minus t square by 2v. Yeah, I think this is so. So, so this just follows from Chernoff doesn't require independence or anything. The whole independence things and multiplicative family and boundedness, all this comes just to get this bound. Once you have this bound, you don't need those things. So A is true, and B, C, and D say only if xi's are multiplicative, only if xi's are bounded, only if xi's are independent. So because of the only if, these are false. Okay. So again, yeah, this is just the application of Chernoff once you have MGF. Um, what is this question about? Okay, this is on conditional expectation. So conditional expectation is used a lot in week three's lecture. In week three, we derive something called Efron-Stein inequality. which bounds variances of quantities like f of x1 to xn, where x1 to xn are independent. So we saw McDiarmid's inequality, which gave a concentration for this kind of thing. But if you want to compute variance of this thing, then we use something called Efronstein inequality, which is covered in this week's lecture. So yeah, and there we use a lot of these properties of uh, conditional distribution, conditional expectation. Okay, so we have these x and y integer valued random variables with joint PMF, okay, and everything. And then we have this new random variable v is expectation of y given x. Okay, and so here v is a random variable. So v is a function of x, right? So you can interpret is that if you fix an x, then v is just expected value of y given x is equal to x. So another way to interpret this is that for every uh, fixed x, okay, you have a distribution of on y given x, right? So this would define a distribution, defines a distribution, and okay, and so expectation of y given x equals to x is just expectation with respect to this distribution, with respect to this distribution. Okay. So the question, expected value of v is expected value of x. So again, this is true by this fact that expected value of y given x, and take expected value of that. This is just expected value of y. Okay, this always holds. Uh, yeah. So okay. Second is expected value of v is expected value of y. So okay. So b is the true option here because we we are conditioning on x, and then we are taking expectation again. So yeah. C is if y equals g of x for some function g, then v is equal to gx. Okay, so we have this fact here that if you have a function of x given x, it's just gx, right? So it is basically so again, like I said last time, given x can be said something like you have already observed some x, then what is your best guess of g of x, right? This is what it says. Expected value of y given x, right? So you have observed x, uh, and y is unobserved. So question is, what is the best estimate of y once observed x? Okay, and best in what sense? Best in mean square sense. Okay, and you can show this that this is just expectation of y given x. Okay, so this is what conditional expectation can be viewed as, and then yeah, so and then this is this property that if you take expectation again, it's just expected value of y. This is called Tower property of conditional expectation. Okay, so in general, what you have, and I'm discussing all this because it's used in this week's lecture. Uh, it is that if you have some random variable y and you have these x comma z, okay, and then so this would be what? This would be some function of x comma z, right? Because you have observed x comma z. This is saying what is your best estimate of y. So it would be some function of x comma z. And if you again take this thing, right? So this would just be expected value of y given x. So right, yeah. So you earlier you were given x comma z. This is your best estimate, and now again now you're given x, right? So you're projecting it on a lower dimensional space. So you could have projected y directly on x. I mean, this projection and all this is like some vague terminology, but yeah, but you instead of directly projecting on x, you first projected on a bigger thing, x comma z, and then went to x. So this tower property says that these two expectations would be the same. So you can either directly go to x, and the special case is like expected value of y given x, expected value of that, right? So this is like expected value of y. So you could have directly gone to this expected value of y, which is like the constant random variable. But first you chose to go to project it on some x, and then you went there. So yeah, some wait, let me see if this is, yeah, I think this is okay. So right, but basically, yeah, this was just some digression, but the C is correct that if y is g of x, then expected value of g of x given x is just g of x, because you have observed x, so your best estimate of g of x is exactly g of x. So yeah, no problem there. Okay, if y is g of x, then b is not defined. Yeah, this is a bogus option. So okay, so 9. Consider the bin packing problem. A bin is a container with a capacity of 1 unit. There are 9 items, and each item size in it is in 0, comma 1.
I think I'm not. I think sync is not there. Are you reading the ninth question?
Oh yeah, I'm reading the, okay. Has it stopped thinking? Yeah.
Yeah, now I am able to see.
Okay. Yes, it's maybe an internet problem on my side. So
Yeah.
yeah. So okay. So you have a bin packing problem. Each bin is of size 1, and the items are of size 0, comma 1. I mean, it lies in interval 0, comma 1. And the goal is to pack these n items using the smallest number of bins. So this is the bin packing problem. The big problem in computer science. You need to come up with efficient algorithms for this. And so, but we are in the stochastic setting. So yeah, let's see what. So okay, so f. So this is how we define f. F is the minimum number of bins required to pack n items. Okay, so for instance, if you have items of size 0 0.4, 0 0.4, 0 0.8, okay, then you need 2 boxes to pack this at least, right? So just pack like item 1 and 2 in the same box and item 3 in the third box. Okay, so item 1 and 2, once you pack, you have like 0.8, and if you add item 3, it would be again 0.8, so totally 1.6, which is not allowed because capacity is 1 unit, and so you need at least 2 boxes. Okay. Um, so this is a deterministic version of the problem, which is a very hard problem. But let's see what we can say if the item sizes are stochastic. So let x1 to xn be IID random variables with uniform 0, 1 distribution. So which of the following are true? Um, so how do it? Okay, so once you have an item, f of x1 to xn, okay, it's less than equal to n. This is okay, right? You have n items, all have size less than 1, so you can pack them in n boxes. This is no problem. Uh, now we want some lower bound on this function. So is it possible to get some lower bound? So one lower bound is like if you have n items, take the total size, okay, and divide by the capacity of the bins. So right, so fx would have to be greater than equal to that, right? So what is this? This will tell you how many bins you require to fill with this volume. Okay, assuming that you could break the items arbitrarily, make them powder and just fit them in the bins, right? Suppose you could do that. Then you would require these many bins, x1 to xn by capacity. But since you cannot break items, you have to keep those items intact. Your fx1 to fxn would be greater than equal to this. So, and capacity of bin is 1 by 1. So you need at least x1 summation x1 to xn boxes. So which means if you just take expectation of both sides, so expectation of f would be greater than equal to what yeah, expectation of x1 plus would be just each is like half into n, so n by 2. So you need at least n by 2 boxes in expectation. Okay, so that is why B is correct. Okay, so C is F satisfy bounded differences property with constants this and this. Okay, so so now again this is clear that if you just change one item, what you need at most, like you need at most one box extra, right? So okay, if you, so suppose your items are like 0.4, 0.4, and 0.8. Suppose you have packed them somehow, then you change just this part, just this item. So if you reduce this item size, it would be no problem. You can stay with the same configuration. If you increase it, then things may go bad. So just take it out and just place it in a new bin, right? And you can always do that, right? No matter, because all the items will be in zero. So F satisfy bounded difference property with C1, Cn. If you change any item while keeping others constant, your F will change by at most one. Okay, and C is a weaker version of that, so C is also correct. Uh, yeah, so okay, so now this is the power of all this concentration inequality and everything, the McDiarmid's inequality, that F is such a complicated function. For every x1 to xn, you will need to compute the best bin arrangement possible. But what you have shown, that you have shown some bounds on the expectation, and now you also know that this satisfies some bounded difference property. So now question number 10 just gives you a concentration bound based on McDiarmid's inequality, right? That even for such a difficultly defined F, you can have very strong concentration just because of McDiarmid. So let's see. So yeah, this is just the derivation of McDiarmid's. How we derive McDiarmid's is we start conditioning on this first I things and define yi as that. So again, you can interpret as that as once you know x1 to xi, what is the best guess of f x1 to xn. Right? So and e of y1 is this the usual expectation, and which of the following are true. So we saw that they form a martingale sequence, right? And then these are just McDiarmid's inequality, right? So this is like you just set it less than equal to delta to get a confidence bound. And yeah, so McDiarmid's inequality is what? It's like e power minus t square by 2 I equals 1 to n ci square, where ci are those bounded difference constants. And here each ci is 1, so you have e square minus t square by 2n. Okay. So this is McDiarmid's inequality, and then this is the confidence version of that. So yeah, I think we are done with all the questions. Do you have any questions from the assignment or
In que- yeah, I
sorry?
have two questions.
Mm-hmm.
Are you able to hear me?
Yeah, I can hear you.
So in question three,
Hmm. Week two,
yeah,
question three. Yes, a Taylor's theorem question.
yeah.
Hmm.
So part B, how like I'm not able to digest the part B, like answer B. In a sense,
Oh,
I think of the function like all the things are equal, like fx equal to zero, then how f(x) going be right?
oh, you mean a constant function?
Uh, then I think it's strict equality in everywhere, or only on fx equal to zero. I mean, I don't get this. Like, can you explain more on?
So if okay, so we know that at zero, the function value is zero, and f dash x is greater than equal to zero, which means that it cannot decrease, right? So that is the intuitive part, that it cannot decrease. Either it will stay constant or it will go up, but it cannot go below this level, the zero level. So which is that fx is greater than equal to zero for all x. If you want to prove it formally, what you can do is that there is something called mean value inequality. Okay, so take 0 here, take x here. We know that this is always true, that fx minus f0 by x minus 0 Okay, what is this? This is just the slope of this thing, right? Fx minus f0 by x minus 0 is equal to f dash of t for some t in 0 comma x. Okay, well, right? So this is basically the basic form of, you can see it as a basic form of Taylor's theorem as well. Taylor's theorem is derived using mean value theorem.
Yeah.
So right, so which means that once you have this slope, there would be some point where this derivative is exactly equal to this slope, right? So that point would be t, and we know that f dash t is greater than equal to 0 for all from this condition, and so this gives us that f.
I was confused in the first part itself because if you put fx equal to 0, then f0 is again the 0. So for any x, right?
uh,
In the left side of inequality in the mean value theorem, the f dash of t is always 0.
oh, if fx is 0, you're saying f dash of t is always 0, is that?
Like from this, isn't it making sense? Like
So
fx equal
it
to
can be
0.
true, yeah, this, so that would be one, but even then fx is greater than equal to 0, that is true, right?
Yeah, yeah, that is true. Yeah,
Yeah.
I mean that is true, but
But yeah, so
that I understood. It's
so
not a, yeah, I
so
understood.
so it's like f of t is f of 0 plus f dash, so f of x is f dash of t for some t in into x, for some t in 0 comma x. So this is the Taylor's theorem, and yeah, and you know that f dash t is greater, yeah, so it's basically, yeah, f dash x can be 0 throughout, so that would not be a problem, but yeah,
Understood.
uh, but but this, for example, this
Yeah,
function,
it's very
right?
very similar. Yeah, yeah.
Yeah, so yeah, it can get confused. Okay, so and what is the other question?
Other question was in week three.
Oh, week three, okay.
Not a, yeah. I mean, can you give me f Constein? So, the definition of f Constein is something like uh,
Oh,
can you
Efronstein's.
give f Constein? Yeah.
Yeah, Efronstein was like, what was Efronstein?
Zi equal to expectation of z given x
Yeah. So variance
equal
of
xi.
z was less than equal to I equals 1 to n. Expected value of variance I z was, I think this was the thing, right? Yeah. So yeah, so I mean, this was the basic form, and then there were other equivalent forms.
No, there I think that I understood like the what derivation and all. So
Hmm.
basically, z equal to function of. Can you write it down?
So z is function of x1 to xn.
X1 to xn,
Hmm.
and then zi is defined as expectation of z given x1 to xi.
Okay.
Uh,
Okay. Yeah.
and then the
So this is something else. This is like this is expected value of, this is expected value of
I understood only ith is a variable.
yeah,
Other
only
things,
I
everything
I changes. Yeah.
ith is a random thing. Baki
Hmm.
everything was given.
Yeah.
Is given.
Hmm. So yeah, so this is one of those things where if you want to compute a variance, you have like, and or it's a function of any independent random variable, then fix all of them and see the variance with respect to one of them, right? Uh, and then sum all of it. So that is what Efronstein gives you. That it gives you that thing formally. So either you can have the worst case thing. So worst case would be what? if you fix everything, what can be the highest variation of the ith random variable, right? Suppose ith random variable lies between a and b always. So the highest variation can be b minus a the whole square, right? That kind of thing. Um, right. So that would be an upper bound. But what this things is a little stronger, that it may not always, you don't need to use the worst case bound, you can use the expected bound, that for some values of other variables xi might not very variation with xi might not be very much, and so you take the expected value over all possible combinations of x minus I. Okay, this is why there is an expectation here. So yeah, just fix all of them, measure the variance with respect to the remaining, and then again fix all of them again, right? So and take average. So that is this quantity, and then do it for all the variables. So that is Efronstein basically. And you can do this for, if x1 to xn are independent, this thing holds. So okay. So again, what was your question?
I only forgot the questions. Give me one moment.
Okay.
So, say that ZI. So can you write it down again? Z0 is defined as expectation of Z.
Hmm. Z0 is like you are given nothing. So what is the best estimate of Z? That would be expected of Z.
Mm-hmm.
Yeah. So again, Z1 is Z given x1 and so on.
Mm-hmm. And then is Z equal to Zn
Yeah. So it would be expected value of Z given everything.
and given everything.
So if you know all the xn's, what is the best estimate of f of x1 to xn, right? You can, it's just f of x1 to xn, which is Z. So this is the thing about conditional expectation, that on this side you can assume that these are given to you and you want to form the best guess of the left side. So if all of them are given, then your best guess would be just directly substitute x1 to xn in f, which will give you Z. So
Mm-hmm.
yeah, so on the other extreme you have like this, where you are given
Need
nothing,
to read.
so take expectation of Z.
I think I have need to read again. It's fine. It's fine.
Yeah, yeah. So you just go through it and you can ask again next time.
Yeah, yeah,
Yeah,
yeah.
next time we'll discuss assignment as well. So okay.
Sure.
Yeah, okay. So
So
let's
this
end this now.
tutorial lecture is like it it has to be every week. Is there any, or whenever you announce, then only it will be happen? It's going to be happen, or it
So
will
this
be
live
any
session,
compulsion? Yeah, live session.
yeah, it would be every Saturday 3 to 4, like it's fixed.
It has to be every Saturday, or
Yeah, it
whenever
has to be.
you announce. Okay.
Yeah, I mean they asked me about my timings, and also for me it was like 3 to 4 was convenient. So
Okay, okay, understood.
yeah.
I thought because there was not announcement or the I think
Oh right, I think they must have forgot. Yeah. So but it's every Saturday. Yeah.
understood.
Okay. Throughout the course. Okay. Yeah. Okay. Yeah. Sure. See you then.
Thanks a lot.
Bye.
Thanks